Namaste friends. In the previous episode, that was Fluid Flywheel Part 1, I talked to you about the fluid flywheel and its principle of working. I talked about the two rotors that were mounted on engine shaft and the gearbox input shaft. These rotors are provided with passages which have uniform cross-section and they are semicircular in shape. The engine shaft and the gearbox shaft rotate but not with equal speed. The fluid, which is in the form of liquid, flows through the passages provided in the rotors. Because the shafts are rotating at different speeds, therefore it can be realized that passage B will not always remain in front of passage A. It will be replaced by another identical passage and fluid will continue to flow in clockwise direction. Well, in the present episode, I will be talking to you about the actual fluid flywheel. As you can see in the diagram, the engine shaft is on the left hand side and the gearbox shaft is on the right hand side. The flywheel, which is mounted on engine shaft, has been provided with a box-like shape. It is integrated with the rotor on right hand side. The rotor on right hand side rotates with the flywheel. Its motion does not affect the motion of the gearbox shaft. The other rotor is mounted on the gearbox shaft. The two are in front of each other. The gearbox shaft, which has been shown in the figure, is able to rotate independently. Its motion is not affected by the motion of the engine shaft. You will notice that there is a gap between the two rotors. This gap is approximately 1 to 1.5 millimeters. The fluid, as you can notice, flows in the anti-clockwise direction. The motion that is available on rotor, which is on right hand side, because of the rotation of fluid, is passed on to the rotor on left hand side, which is mounted on gearbox shaft. In the previous episode, we have seen how the transfer of energy takes place. It is also known that the speed of the gearbox shaft will not become equal to the speed of the engine shaft. Because if that happens, there will not be any flow of fluid in the passages and transfer of energy will not be possible. So the two shafts are rotating at different speeds. Now the gap between the two rotors, which is about 1.5 millimeter, allows the fluid to escape through it. The fluid moving in counterclockwise direction moves upwards because of the centrifugal force. It accumulates at point X and maintains a pressure that prevents further escape of fluid, and it will continue to flow in anti-clockwise direction from passage provided on right hand side rotor to passage provided on left hand side rotor. So this is how the actual fluid flywheel works. Now, next thing that we have to take up is the characteristics of fluid flywheel. For this, we have to consider a graphical representation which has been shown in the diagram. Now, in the diagram, on vertical axis, you will find the percentage slip. Now, the slip is the difference in speed between driving shaft and the driven shaft. In our case, the speed of the driving shaft is capital N RPM and the speed of the driven shaft is small n RPM. Therefore, slip is represented as capital N minus small n. Now, because we consider the percentage slip with respect to the speed of the driving shaft, therefore, the percentage slip is given by capital N minus small n divided by capital N multiplied by 100. Now, if the speed of the driven shaft, that is small n, is 0, this means that percentage slip is 100. On the other side, if the speed of the driving shaft and driven shaft become equal, the percentage slip will be equal to 0. Now in the graph, the x-axis represents the speed of the driving shaft. The values that you find on the x-axis in the form of 1000, 2000 and up to 7000 are for a particular engine, and these have been assumed to understand the variation in percentage slip with the speed of the engine shaft. The values that have been shown on the x-axis may vary from engine to engine. Initially, it can be observed in this case that with engine speed or the speed of the driving shaft between 0 and about 400 rpm, the percentage slip is about 100%. This means no motion is transferred to the gearbox shaft and it is the disengaged position of the clutch. Further increase in the engine speed to about 1000 rpm, we find that the percentage slip goes down to about 5%. And as the speed of the engine shaft further increases, we have lowering down of the percentage slip, which becomes minimum, that is 3%, when the speed of the engine shaft is about 7000 rpm. So the minimum value of percentage slip remains 3, which indicates that two shafts are not rotating with the same speed. The percentage slip at any engine speed, however, depends upon the torque being transmitted. This curve is based on the assumption that engine exerts full torque at every speed. In this example, we find that the slip percentage is considerable up to an engine speed of about 400 rpm. This is comparable to the slipping of ordinary clutch, which causes the excessive fuel consumption. The ordinary friction clutch would have been damaged because of this slip. In case of fluid flywheel, this energy is converted into heat, which makes the fluid flywheel hot. Well, this was about the fluid flywheel. Thank you very much for watching this episode.